a moment. Yeah.
Sure.
Okay, so according to YouTube, we are now live, so you can get started whenever. Yeah.
Okay, so one more day of NIM for us. And I think most people here have been listening in, but it's all right. It's still standalone, so it's okay. Okay, so the book we're reading from today is Penrose Styles to Trapdoors and Ciphers, and the article is on Withoff's NIM. Okay, so what's going on? So essentially, imagine a chessboard, and there's a queen sitting somewhere up on the top row. Uh, and then now this queen is special in the sense that it can only move to the left diagonally. So to the, what would that be? The west, the south, and the southwest, right? And the aim is to try to get the queen to this corner spot here. The question is, can the first player get this queen to this position if these are the movements allowed? And yeah, of course, everybody is welcome to if there are any thoughts. So again, the piece moves like a queen. On your turn, you can move it as far left, as far diagonally, as far to the south, as far down as you like. The question is, who's going to be able to get it into the starred position? Well, and maybe what we want to do is systematically go over the board. Okay, so let's consider the positions right next to us. So supposing your piece started in one of these positions. On your turn, would you be able to get it into the corner? Does anyone have a thought? Yep. All right. Wonderful. And maybe we can extend that a little bit. And you can see that the queen can move all the way left. So anything on the bottom row, anything on the leftmost column, and anything along the major diagonal, along this diagonal, are obviously going to be positions that the queen can get to in just one go. Okay, so that leaves us to think about, what about this position here? If the queen was sitting there, is there anything that the first player could do to get the queen right into this? And again, remember, you can't move upward or rightward or diagonally to the northeast. So, well, all you're left with, all your options, involve you moving to a position from which on the next turn you'd be able to get to the corner. Oh, yes, sad, yes. Okay, so yeah. So Neil says it's a sad board. And symmetrically, so is this position. Okay, so I'm going to, well, what about a position right next to this sad position here? If it were my turn, I'd move into the sad position, knowing that there's nothing you could really do to prevent me. You'd have to move into a position that's good for me. Yeah, and again, please do stop me if some part of this is not clear. I'm just going to assume until someone says something that this is making sense. Okay, so remember, these were good positions right from the beginning. These were not. Okay, so all right. Then now I'm going a little too fast. Hold on a moment. So consider this position we've just figured out is not very good. But anything on this row, this column, or this diagonal could get me to a position that's not an immediate win for your opponent, right? So anything on those lines would involve trying to move to this circled position here. So all those would be a good place to be in. So if you're able to move your piece into a position that's guaranteed to be like a place from which your opponent can't immediately win, those are things you want to do. So you're looking for moves that could get you into these positions, and you just follow the same strategy. So you keep arguing backwards. So here and here, Yeah, sorry, I've got one more thing to go. So the diagonals from this one, the verticals from this one. So I should have filled in all of those. I think perhaps I will. Sorry, I should have filled in. Okay, hold on. Am I making this worse? Or
No, I think but what was on the slide was just fine, I think.
yeah. Okay. So
Hmm.
essentially go to the place you cannot achieve, look along the diagonal position from there, the horizontal positions from there, vertical positions from there. Those are all places you'd like to be. Fill in the board. When you can't go any further, well, those are not happy positions. I said, no, sorry. Well, Neil, the happy sad is getting me. But all right, so I'm trying to practice for Saturday and still. So this is a position I would like to end my turn on. If I get here, I'm happy because I know that no matter what you do, you're going to end up on one of the positions from which I can win. All right. Anyway, so this, well, it does look a little bit as if there's some sort of pattern going on here. So if you look symmetric to this diagonal that I've tried to put in a different color, these lines, I mean, seem to be, it seems to be reflecting along this line. Right? I mean, this is a little perhaps early to say there's a pattern, but if you were to continue, perhaps you have a program that lets you figure this out on a much larger board. It turns out that there's this kind of distinctive pattern, two lines apparently showing up. So the question is, what's special about these lines? Okay, so it is going to feel a little miraculous, but let's. Okay, so again, so I promised you a game of NIM and I'm talking about queens moving around boards. So let's talk about the isomorphic NIM game and let's see why it's exactly the same thing secretly.
So, but yeah, is it clear? I mean, these are lines. Kya matlab, is it kind
Yeah,
of?
apparently you can zoom out as much as you like, and these are going to turn out to be lines. In a minute, I'll tell you about their slopes and whatnot. But it's going to turn out that if you,
Oh, so that's actually a line. Okay, all right, cool.
yeah, I mean, yeah. So, yeah. Okay, and then suddenly, look, they go through the origin. So there's no intercept, but there's some kind of a slope.
Yeah, I mean, I think the symmetry is very evident. I was just making sure that there's a line equation there, but yeah, I suppose there is. So yeah, cool. Thanks.
Yeah. Okay, so the corresponding NIM game goes something like this. There's two piles of tokens. So this is again, like we were talking about last week, couple of rows, some tokens in the first row, some tokens on the bottom row. The difference here is that you're specifically playing only with two rows of counters. You can, as with NIM, take away at least a counter. You're welcome to empty out a row. But you can now, there's one more little wrinkle here. You can take tokens from both piles with the condition that you take the same number from both the rows. Now, with this, does anybody see why this is the same as the previous game? Let me try to take us back here. So why are these two things really the same?
So if you give me a second, I will put these rules in the chat so that you can move back.
Oh, thank you.
Yeah, just a minute. Yeah, I think I have it. Yeah, okay, thanks.
I guess I suppose that chat messages you. All right, okay. All right, so now, well, why is it the same thing? Well, think about this x coordinate here as one pile and the y coordinate is the other pile. So if you move, maybe I should have gone back to the earlier chessboard. But anyway, so reducing the x coordinate, which is one thing you're allowed to do. Reduce the y coordinate is the other thing you're allowed to do. And reduce both equally. So that's kind of like.
So I think there's a comment in the chat, which is perhaps exactly what you just said,
Exactly.
but yeah. Read it out.
Yeah. And so because of this, so they're basically the same thing just slightly in disguise. So if you can figure one out, you can figure the other out. And I'm going to run through some ideas that will need a lot more building up, but I'm hoping that people will be inclined to go read about it after, because, okay. Okay, so if you write out, oopsie, if you write out the coordinate positions, I'm going to just write out, okay, so because they're just a reflection, so these other ones, so this one here, so if this is 1, 2, well, this one here is just going to be 2, 1, and you can read this off as well if you want, but this is just going to be, 2, 1. So I'm not going to worry about them. So if I can figure one of the lines out, I'm going to be able to figure the other one out as well. So let's see that something kind of, I mean, at this point, it's going to seem a little miraculous, but let's, okay, so let's look at what's special about these positions, all right? Okay, so I've listed out the ones that you could put on the 25 by 25 grid. You can keep going, there's nothing. So it's just these coordinates that I'm picking up. So what I'm calling the A sequence, or what Gardner's calling the A sequence, is just the X coordinate of these positions. And the corresponding Y coordinates are what he's going to call the B sequence. Again, well, let's start with one interesting observation. If I were to just look at the positions, if I just were to count off, if I were just to go 1, 2, 3, etc., that's what this is. It's going to turn out that if I were to add the position to this, sorry, hold on, difference. Yeah, exactly. The difference between the Y and the X turns out to be the P. And this is something that's actually not that hard to see, but I'm not going to do it. If anybody wants to know this, I can. Yeah, exactly. Except, oh, I changed my mind and called this A and B, which I forgot to update. I'll update before I put it out. But, and then, I mean, this isn't even, to see the actual convergence, you'd have to do a much larger, essentially the slope is going to tend towards, okay, so if I had written out instead of these numbers, if it had been 1.618, this is one of those numbers that shows up all over the place. And I just wonder if anybody recognizes it. Yeah. It's one of those things that anyway, so yeah, so it turns out that the slope of this line up here, this line up here is going to be the golden ratio for some. I mean, this is so the article says that he pulled it out of a hat, and it does feel a little bit like that. But at this point, it's observational. So, okay. So the way these numbers, so this is something called a BT sequence. So what's going on is that this irrational number, this is something like that, right? Something like that. Unless I mucked up, isn't that what it is? Something like that. Yeah, I'm hoping that's right. So essentially multiples of this, I've tried to calculate them out here. So you take n, just increment, just take the counting numbers, multiply 5 by them, and then take the floor. So essentially take away everything after the decimal point. And that's how you're getting these guys here. Okay, so the ones on the top row, the A sequence. So that is the A sequence. And if you look at it, okay, so if you look on any row or column, there's only one of these unsafe positions, right? And so every natural number is going to show up on either, it's going to be either in the first sequence or in the second sequence. And okay, so I didn't tell you how to get a hold of the second sequence, where you do the same thing with 5 squared, right? Yeah, so this part of it does seem a little miraculous. There's something you can do with it, but this is really not what I wanted to focus on. So let me run through this and say one more apparently interesting thing. So today is just going to be, yeah, wonderful. Yeah, exactly. Okay, so if you look at, it does look awfully like we're listing out the Fibonacci sequence. So 1, 2, 3, 5. Well, there's a little blip here, right? What's that? So we're about to see it's white. So it is almost a Fibonacci sequence, except there's all these interesting things happening in between. So let's see. Okay, so all of these. So if you took the Fibonacci sequence and you grouped things up like this, well, turns out they're all safe positions on the board. Well, what about these guys? Where did they come from? Well, interestingly, what if I were to start a new, so basically start your Fibonacci sequence from here. So add 4 and 7 to get 11, 7 and 11 to get 18. And that's how you get hold of some of them. And you keep on doing this. Make the same argument over again every time you see a new pairing. Yeah, exactly. All right. Yes. Okay. All right. So now the question is, well, all this is well and good, but if you wanted to play a game, how would you go about winning this game? So let's just quickly take this and see whether there's a way to look at a couple of piles. So like if I give you, say, the piles that we started out with, let's go back and look at the NIM game we started with. So there's a pile with 3 and a pile with 5. And well, 3, 5 actually showed up in this. So you automatically know that if you were given this state, if you were given this state, what would you do? You would be in trouble. So if you were able to give someone the state, you would be happy. All right. So, well, what if I give you something completely different? What if I didn't give you one of the ones that we've just identified? How do you go about, so again, if this were a very large game and you didn't want to either draw these lines and find all the points, make the tables, so if not recursively like this, is there a way to look at a couple of piles and say whether it's a safe or an unsafe position? And for this, I'm going to have to do something that is going to be slightly faith-based. But the idea is that any number can be broken up into a combination of Fibonacci numbers. So for instance, if I were to write 17, which is not a Fibonacci number, but as 13 and 3 and 1, well, I'm going to use this sort of a representation where I'm kind of going to say, so if this is present in the decomposition, then I'm going to say 1 here. If not, I'm going to put a 0 in. So the representation for 17 in this new notation is going to be 1, 0, 0, 1, 0, 1. Okay, and this is to tell you which of the Fibonacci numbers appear in the decomposition of the number you're interested in. Okay. How does this help me any? Well, turns out there's a really sweet pattern here. So if you look at these guys, right? If I look at these fellows, well, what are they in terms of, they're just the Fibonacci numbers, right? So they're 1, 1, 0, 1, 0, 0, keep going like this. Oh, okay, all right. What about these guys? Well, if you look at 4, well, that's 3 plus 1. So 1, 0, 1. And then with the 7, you add in a 0. So there's this very interesting pattern that you start off with some sort of a seed and then you keep adding zeros to it and you generate a whole entire sequence of numbers. All right. Yeah, and again, I think I'm really running through this because, all right, so. Yeah, and I think this is a Zakendorf representation, right, Neil? Yeah, but this idea that you can write them out on a
Correct.
yeah.
And I suppose non-consecutive or something, right?
I don't know that they've used that, but I guess if it's Zakendorf, it's non-consecutive. Well, if it was not, if it was consecutive, it would just be a Fibonacci, the next Fibonacci number, wouldn't it?
That's correct. So it would therefore not be unique. So if we are claiming that the representation is unique, I think we would need.
So that's to achieve the naked unique. So I guess the reason that this is the 2, or rather 3 is 1 0 0 rather than 0 1 1.
Right, exactly.
Okay. 4 is 100. Well, no, it would be 1 0 1, wouldn't it? Because 3 would be 100. I mean, or rather, not 100, but 1 0 0. 5 would be 1 0 1. Well, are you writing it in binary?
Binary, yeah.
Because this is not binary. The basis I'm using is a Fibonacci, not powers of 2. Right? So again, so what you're doing is you're writing out all the Fibonacci numbers, identifying which ones. Yeah, so Shashi, do you want to unmute and talk to me? 5 is 10, 5 is 1 0. Yes, exactly. Oh, wait, hold on. 1 0. Wait, 5 would be 1 0 0 0. I was just happy that it was. So 5 isn't 1 0. Are the question marks 0? So I mean, yeah, it sounds like this isn't making much sense. So could you unmute and talk to me, please? Ravi, Shashi, if you wanted to.
Yeah, bottom 4, 7.
Yeah. Yes.
Yeah.
What about it?
101. Bottom line.
Yeah. So 4 would be 101, right?
Yeah.
Yeah. And then 7 would be what? 7 would be 5 plus 2. So it would be, if I were to write out 7, it would be that, right? 5 plus 2. So 1 in the 5's place, a 1 in the 2's, 0 for the 3 and the 1. Yeah? How are we confident this generates unique resonance? Yeah, well, okay. So that's the part I'm sort of brushing under the cover. You can prove that. If you want to look it up, it's something called a Zakendorf. I never
think it's
know.
also like a nice exercise. You can try to argue using contradiction, induction, or some combination of those techniques. So I think the fact that you can always represent a number as a sum of non-consecutive Fibonacci numbers is kind of using induction. Try to remove the largest Fibonacci number that you can, and what's remaining you can sort of recurse, something of that sort. And then I think you need to set up an appropriate contradiction if you say that it can be done in 2 ways. It's not, I mean, yeah, it's a cute, I think it's a cute exercise. So maybe we give ourselves a chance to think about it, and we can always discuss it in a future meeting if that works.
Yeah, thanks. Yeah, but the question's really good that you do need to argue that. I should not have just jumped over that like that. What is happening in chat? Okay. Okay, anyway, so now, well, I've still not taught you how to play the game. So I've given you all this lot of information, but if I were to give you if I were to give you a board state like this, so 10 counters in one pile, 15 in the other, would this be, so I was going to say, can we try this out together? So would this be a safe position? If so, what would I need to do? What would I need to give you to be sure that I'm going to win? First of all, is this one of the ones we saw? Well, no, right? Let's just, yeah, okay. I don't want to go back. I can go back and show you, but for a minute, could we, there's one more cute thing that we need to notice from the previous, hold on. Oops. Okay, so the other thing, let me just erase all this mess. Oopsie. Okay. So if you look at the first number in each of these sequences, okay, so the argument is, well, any number is going to show up either in the X or the Y position, right? This is because we've already said that every number is going to appear somewhere and only once. So the argument is that if you, well, this is a little hard to see, so maybe let's not use these. We'll come back to these ones. Oops. Okay, so let's use these, the ones I've underlined. And notice that there's this interesting pattern going on, that if it's an A number, so to an A number, I attach a 0 on the extreme right, get the corresponding Y coordinate or the B sequence number. And if you were to count the positions before, so if you go, so the rightmost one that appears is going to appear after even numbers. So if I go 1, 2, and then I see a 1, here I actually go 0, and then I see a 1, 0, and then I see a 1, 0, and then I see a 1. So those are all even. And if I look here, it's like, it's going to be the same thing because I'm just attaching zeros to the back of it. Here too. So the argument is that there's a very nice way of telling if it's a one of the A positions. What you need to do is to just check if the rightmost one is in an even position. So if there are even digits to the left of it. So now if I go look at this, what I'd like you to do is to try to write it out as a combination of Fibonacci numbers, and basically tell me what the Fibonacci representations of these two numbers are.
Do you want to go back to some of the example representations, maybe? I don't know if that's...
Yeah, so you've got the numbers 10 and 15.
15.
Let me go take us back here.
And 10 is already there, I suppose. Okay.
Yeah, if anybody wants it, yes. Okay, so the pairing that I require notice this pattern that I want whatever appears in the X, I would, again, when I say X and Y, what I'm assuming is that this is the smaller number. So the X or the A, this. So I'm writing my sequence out so that I mean, I don't know that it's an A and B, except in these cases, I won't write that. But essentially, write your sequence, write your position out with the larger number following the smaller number, because that's the line we're looking at in this work here. And try to write them both out in terms of Fibonacci numbers. Okay, I don't know if anybody's trying to get 10 and 15 out of this. If you need me to run over it, I'm happy to, but I would really like to know where people are stuck. So, right, so the way I would do, okay, let's start with the 10, right? Okay. It's tough, all right, okay, so let's do it together. So for instance, 10, so what's the largest Fibonacci number less than 10? Yeah, okay, so I guess the 8 is an answer. So I think there's one. Okay, let's just do them. So okay, so this would be 8 and 2. Yep. Well, that would mean, I just cut this out. Okay, I'm going to write out for the number 10, a 1 where the 8 is, no 5s, no 3s, a 1 for the 2, and no 1. Okay, so it'll be 1 0 0 1 0, which I think I did see. I think I mucked up when I typed it out. Maybe my 6 was wrong. 1 0 0. Yeah. I don't know where I got that from.
So I thought you said that when you represent numbers with Fibonacci, the numbers cannot be consecutive, right? In which case you can't get two ones together, no? So what does it mean for 6 to be 1 1 1?
Yeah. I don't know what I was thinking. So this is just nonsense. I have no idea what I was thinking. So I think I just had some sort of, and 1 1 1 doesn't make any sense. You can't have the ones next to each other. I have absolutely no idea where I don't know what I was thinking. Maybe I went 3 2 1. Yeah, clearly I wasn't thinking. So this is nonsense. So it's a good thing. Let's do it again. And then with the 15, what do I do? I think perhaps at this point everyone's already got it, but it's the 13. Yeah, so in order to make it unique, I couldn't do what I just did here. So I would like this to be 13 and 2, which would be 1 0 0 0 1 0. Yeah, and I think, yeah, Herschel's were right. 1 0 0 0 1 0. Okay. Yeah. All right. So then would this pairing of 10 and 15 be a pile you'd want to, like, would this be a safe board state to give someone else? So is this what you aim for? Yeah, I'll correct this before I post it. Yes, no, maybe so. Well, no, because all of them, whatever I have on the X, I'd like to have a 0 appended on the right. Yeah. Okay, so there's two things I could do. I could either take from the 10 pile or from the 15 pile. Oh, yeah. Okay, so apparently I did it here. All right, so now we'll pick one. What if I were to decide, okay, so is 10 an A number? Well, yes, because if I look at the rightmost, let's just count 1, 2, okay, so I'm going 1, 2, 3, 4, 5. Okay, so, and in this case, 2, it's 1, 2, 3, 4, 5. Okay, so it isn't. So what I do is I count the number of digits So this is actually not any number, right? So I would like it to be a comma something. So if you go back and look at the sequences, I think we already just saw it, 6 and 10. So 10 did not show up in sequence A, it showed up in sequence B. And we know this because we counted off and we saw that there were an odd number of digits before the rightmost one. So what we, from this itself, can probably figure out that we want to mess with this pile. And we really do know, and we know what we want in that pile. Well, we want to take away a 0. So we want to go, so we would like to have 1, 0, 0, 0, 1, which is best. Just all I'm doing is I'm reading off this number for 15 and I'm removing the 0 at the end, which I probably shouldn't do like that. But I'm essentially writing the same number out without the leading 0, which means this is an 8 and a 1. So I would like this to be a 9. So I take 1 token from the first pile is one way to make this safe. And we could go back and look. Yeah, here you go. Yeah, so this would be a pile I seek. So I would remove 1 token from the first pile. Okay, this is pretty much all I wanted to say today because that felt like a lot already. Yeah, I don't know if it made any sense, but perhaps an incentive to go read a little more and think about it. And maybe read the article too.
So I don't know if you don't mind, like, can we do a 5-sentence summary of the whole thing starting?
Yeah, sure, absolutely. It did feel like a lot of strange stuff happening, right? So let's run over it.
Oh, no, not for that reason, just because it's fun.
All right. So essentially, we started off by looking at, oops, I don't know how to get to the front of this thing. Okay. So we started off by looking at a game on a chessboard. And we said, look, there's a queen sitting on the top. And it does not matter that this board is an 8x8 chessboard. I could have chosen to do this on any sized board. If this queen, and I really like how Bergkamp explains this, he says that this chess piece has been struck by a diagonal plague and is no longer allowed. So after some illness, the poor queen can't move in all the directions she could. She's now confined to move only to the west, southwest, and the south. And the question is, can we move her into the bottom left position of the board? And then what we did is we went and we looked at the board and argued with these allowed movements. We argued that unsafe positions showed up in a very specific sort of pattern. So anywhere outside of these black squares, so the player who's able to move onto one of these squares would win the game, because from there, there's a move to victory. After that,
so at this point, if you projected all the shaded squares onto the x or the y-axis, you get the Fibonacci series. Is that the pattern?
yeah, exactly. That is what, yeah, here it is.
Correct.
Yeah.
Yeah, you had it quite explicitly, yes.
Yeah, but I mean, we didn't know why it was there, but maybe the recap is good for that reason. And then the argument was, well, this is secretly just this a NIM game, this other NIM game in disguise. And the difference between this and the regular game of NIM is that now you're allowed to take from both piles, which is really the diagonal action of the queen, right? So it's not just reducing counters. So reducing counters from pile 1, for instance, would be just moving down a column, say, and reducing from the other pile would be just moving leftward along a row. And the reason it's symmetric is really, so the reason that these two lines are symmetric is also because who knows, pile 1, pile 2, right? The argument should hold whether you work with pile 1 or pile 2. And as you can see, you've got these nice two symmetric lines show up. And then there was this mysterious, well, it's all actually the Fibonacci, it's all the golden ratio. Yeah, I don't want it. Maybe all right. And then, well, because if there's a golden ratio, why stop there? There's always a Fibonacci following. And then we said, well, one way to actually look at the board state and decide how to proceed, whether you want to, how to play the game, really, like would depend on whether the number of tokens is not just Fibonacci, because while some of these numbers directly appear on the Fibonacci sequence, there are more numbers than appear directly in the Fibonacci sequence, because remember that every single number has to show up in one of these two sequences, either in the X or the Y coordinate of one of these safe positions. You would like every natural number to show up. And so then we went ahead and determined how to decide except for some explicit brain part here, we decided how to play the game. So we turned this back into game strategy after some excursion into BT sequences and Fibonacci numbers. Okay, so I think I don't know if that was much of a summary, Neil.
Okay, that was perfect for me. Yeah, and for everyone, it looks like. Thanks.
All right. So yeah, so I would say go read the article, because this is my short summary of a lot of stuff going on in this particular one.
Yeah, okay. The representation is well defined.
Oh no, so okay, so yeah, uniqueness we imposed that
I mean, that does require an argument. I don't think it's kind of obvious, but there is an argument. So yeah, I guess, yeah, is the representation yeah, so no two natural numbers will have the same representation clearly, because once you fix a representation, it'll sum to one particular thing. So you cannot have two things having the same representation. On the other hand, you could ask if one thing has multiple representations. Maybe that's your question. But again, if you don't impose non-consecutives, then you lose that. But once you agree that you're going to represent your number as a sum of non-consecutive Fibonacci numbers, you do get uniqueness as well. So what we were saying earlier is that that's like a nice exercise to walk through. But in one of the future sessions, I think we can also walk through a proof. But it's just nice to think about once before.
yeah, I mean, and even the article does say that how did this, so apparently the original article, somebody called Isaacs, and he says he pulled it out of a hat. So I think it's one of those things where observation of the pattern led to the rest of this. It's quite a neat. And I think,
Yeah, I mean, when you see something that's so neat, you sometimes wonder if somebody kind of had the end game in mind first, and then they reverse engineered a rule set that would lead to this analysis. But that seems hard here.
Well, I think also,
yeah,
I think the cornering game existed prior to Vitaf and the NIM.
I see. Interesting. Yeah. Yes. This is really, it's pretty magical that these patterns show up. The strategy is really cool too.
Yeah. But I mean, in all your usual suspects, right? I mean, golden ratio.
Yeah. This is true. All right. So unless there are more questions or comments, I don't see anything that we have missed in the chat, hopefully. You just give it 30 seconds if somebody wants to unmute and say something. If not, this seems like a nice place to wrap up and to say that I'll meet tomorrow, the same time, the same link. Yeah, cool. All right, then thanks everybody for joining in. The website will be updated shortly and see you back tomorrow. Good night, everyone.